everyone. This is the last section in this chapter on polynomials, 5.9, and we're done after this. And what we're going to talk about in this section are transformations of a polynomial and what they would look like and how you would do it. So if I take this parent function like this one, y equals x cubed, how could I transform it in many, many different ways, and what would it end up looking like? So that's what we're going to deal with in this last one. So let's start with this one. We're going to take this parent function, y equals x cubed, basic cubic function, and we want to perform these different transformations onto it. How would that affect the equation? And we'll take it a step at a time. So the first thing is we want to vertically compress this by a factor of 1/2. So if we took this and we applied a vertical compression by a factor of 1/2, then all we would do is multiply this by 1/2. It's very similar to a slope. So that would be, well, let's just do this right here. Y equals 1/2 x cubed. So that's the first step. The next thing is now we want to reflect it across the x-axis. So if we are reflecting it across the x-axis, then that means our x's don't change, but our y's do. So we are basically going to multiply this by negative. So that is what would happen. This becomes negative 1/2 x cubed. That's what that does. Now we want to go 3 right. Okay, 3 right is a horizontal translation, and that's with the x. The x gets shifted 3 to the right. So my x becomes x minus 3. Remember, we're going to do the opposite in horizontal. If I want to go 3 to the right, then I got to go x minus 3. It's sort of like the factors and the zeros type of idea. So this x becomes x minus 3. So y is negative 1/2, and our x goes from x to x minus 3, and that's how you would do that. 3 to the right. And then 2 up, we just add 2 at the end, and we're done. So this is this equation compressed by a factor of 1/2, reflected across the x-axis, shifted to the right 3, and 2 up, and there's our equation, and you're done. Not all cubic functions, we can't do this with all cubic functions. This is just the basic parent cubic function that looks like this. If we had a cubic function that looked like this, there's no way that we're going to be able to do these kind of things. But some of them we can, and those that we can, we will. So this equation here on the board represents all the different cubics that we can transform just by compressions, reflections, translations, to the left and right and up and down. They would be able to fit this format if we are able to do that. And this looks a lot like quadratics. When we did quadratics, it's just only a difference of a 3rd degree instead of a 2nd degree. I'm going to give you your got it question a little early in this video. Please do not be tempted to stop, because you know I have a whole lot more to show you. I just thought this would be a great lesson check question, something you could do. Let's take this parent function, y equals x cubed, this cubic, and I would like you to tell me what would its equation be if you stretched it by a factor of 2 and you translated it 3 left and 4 down. What would the resulting equation be? Turn that in to show me you watched this video. That'd be great. Okay, you may be asked how many zeros a cubic has. And so you see, here's my basic equation. So if a and h and k are all real numbers, and a is not a 0, by the way, so this is a number 1 or whatever, some kind of number, then how many zeros, how many distinct real, not imaginary, distinct real zeros would this function have? And you may think, what in the world do they mean? So I'm going to show you, we're going to do that even with these letters. I'm going to change, since we're wanting to know how many zeros it has, I'm going to change this y to a 0, and then we're going to solve for x. So the first thing that we would do to solve for x is subtract the k, move it to the other side. Our next step to isolating x is to get rid of this negative a It's being multiplied, so let's do the opposite. Let's divide both sides by negative a. Now I need to still get this x by itself, but it is being raised to the third power. So we need to undo that third power. So the opposite of powers are roots. So we're going to take the cube root of both sides. All right, and now to get x by itself, all I need to do is add h to both sides. Now you still may be looking at this thinking, how in the world did this help me? I mean, these are just a bunch of letters. This doesn't mean anything. But actually it does, because my question was how many real zeros would this have? And this could only represent one number. There's no plus or minus or anything like that. There's only going to be one cube root of this plus this. So there's only one real zero in this type of equation. So now that we've walked through those steps with letters, let's walk through those steps with numbers and answer this question: what are the real zeros of this transformed cubic equation? So we'll go through the same steps. We'll start by making this equal to 0 and then subtracting 6. Next, we'll divide both sides by 3. Now we'll take the cube root of both sides to get rid of this third degree. And now we'll add 1 to both sides. And we get x equals 1 plus the cube root of negative 2. Or you could write it minus the cube root of positive 2, because negative numbers do have one cube root, right? So it could be written either way. This looks like the way it would end up. I saw that in the book. They both will turn out to be the same, but that is your number. That is your one real zero. All right, just as not all cubics are just basic translations, some of them are more complex. The same is true with quartics when we get into 4th degree polynomials. And you're going to be asked to come up with some quartic equations that have been translated or transformed. And you might want to say, yikes, how in the world am I supposed to do that? I'm going to show you, I'm going to try to walk through the example that's in the book, try to explain how they got there, and then I'm going to show you another method to do the same thing, which I think is a lot easier, and I would recommend because they will both work. But they ask you to write a quartic that has real zeros of x equals 5 and x equals 9. Those are its real zeros. What would that quartic be? And yeah. So they ask you to do it showing transformations. First way is to show transformations. So if you look at 5 and 9, you realize those two zeros are 4 units apart. So what you can do is start with the equation that has zeros at -2 and +2, because those are 4 units apart and we want plus and minus the same number. So I'm going to just take this and go all the way back to the two numbers that are 4 units apart on either side of 0, and that would be plus or minus 2. If you get this, great. So that means x plus 2 and x minus 2 would be 2 of the zeros, which means that's x squared minus 4, right? So if they ask for a quartic that has that, then they would have this. So to get to the basic quartic, they took x squared minus 4 and they just squared both of those to x to the 4th minus 16. So x to the 4th minus 16, which is basically x squared minus 4 times x squared plus 4. That's the tricky part, which is why I'm going to show you an easier way in a minute. But now I've got this basic parent function, x to the 4th minus 16, and I want to shift it here. If we look, we started out with a 0 of 2. This represents a 0 of 2. And we want a 0 of 9. So if I go from +2 to +9, that's 7 units to the right. So I want to take this and translate it 7 units to the right. So what I'm going to do is, instead of x to the 4th, it's going to be x minus 7 to the 4th. And there's my equation. Now I thought that was complicated and somewhat difficult. So let me show you another way. Instead of having to find the parent function and then use translations or transformations, let's just use algebra. If I know I have, these are two zeros, then from these I can get their factors. Remember, the factors are x minus the zeros. So this would be x minus 5 and this would be x minus 9. Those are two of my factors. Now that gets me to a second degree, but remember it asked for a quartic. I need a fourth degree. These are my only real zeros. My other zeros are imaginary. So what I'm going to do to get those two extra imaginary ones is I'm going to use x squared plus 1. Remember how that factors to x plus I, x minus I? So this can represent my two imaginary factors. Now all I have to do is multiply these things together, which may make you say, what do you mean that's all I have to do? But you've done this kind of stuff before. So I'm sure that you can handle it okay. So first FOIL this. This is x squared minus 14x plus 45, and then multiply that times x squared plus 1, and you'll end up with a fourth degree polynomial with these two real zeros. So I set them up this way, multiplied all of this by 1, and then all of these by x squared, being careful to stack under like terms, and now I just add, and I get x to the fourth minus 14x cubed plus 46x squared minus 14x plus 45. There's a quartic with these two real zeros. So the two factors, these give me my two factors. Just use x squared plus 1 for your other two and multiply them out. And now you're using algebra instead of transformations. And there are a lot of possible quartics, obviously, that have just those two. But those two methods are the easiest way to come up with them. Okay, I want to spend just a couple more minutes talking about power functions. Have this in your notes, power function. So a power function is when your x is the base of an exponent right here. That makes it a power function. So this is the basic format of a power function. You have some number times a base of x to some degree. A and B are real numbers, nothing imaginary. They can be decimals or even negatives, but this is a power function. And this works a lot like a direct variation did. So we have, just like we did direct variation when this was x squared, you can have the same kind of relationships with different degrees other than just a squared. So let me show you how that works and what I mean by that. Okay, here is a function that represents the power generated by a wind turbine. Now, my sister lives down in California, and not too far from her are just acres and acres of what look like to be bare land filled with these great big giant turning windmill type things. They are electric power generators. They're trying to use the wind to generate power. This would be an equation for those wind turbines of the power that they can generate. P represents the power in kilowatts, and V is the speed of the wind or the air in meters per second. So we take that speed and cube it. Remember, exponents go first, so speed to the power of 3. And this A is our constant of proportionality, like we had with direct variation. I said was similar to slope. Exact same idea. It's just now we're dealing with power instead of just a single x or even an x squared. So we're going to look, so this is our basic equation. Okay, so the particular example in the book says that one of these wind turbines generates 600 kilowatts of power when the wind speed is 8 meters per second. So now if you have that relationship, how much kilowatts of power will it generate if the wind speed is 10 meters per second? So here's how you will do it. You will take the information that you have, this is just like you did with direct variation, and you'll plug it into this basic equation. Our power is 600 So it's 600 when our speed is 8. We don't know what A is. So that's what we need to solve for. We need to solve for this constant of proportionality. So to solve for A, I'm going to divide both sides by 8 cubed. So 8 cubed is 512. So 600 divided by 512 is about 1.1719. Feel free to go out this many decimal places. That's legit. So about 1.1719. Now we can make that our A and solve for how much power then would be generated when the wind is going 10 meters per second. So here we plugged in the 1.1719. 10 cubed is 1,000. So if I multiply this by 1,000, I am just moving this over 3 places. And so we realize the power generated would be about 1172 kilowatts. Round it to the nearest whole number instead of 1171.9, about 1,172 kilowatts when the wind is 10 meters per second. Notice that's an exponential growth. The faster it is, it's an exponential growth in the amount of power generated. We went from 600, just by going up 2 meters per second, we went from 600 kilowatts to over 1,100, almost twice as much, just by increasing our wind speed by 2 meters per second. This could be a second lesson check, if you'll bear with me, just to try it. It'd be worth it, and then you can check with me and see if you get it right. But let's use this same basic power function. P equals A times V to the power of 3. Let's say I have a different wind turbine. It generates 210 kilowatts of power when the air speed is 12 miles per hour. So not meters per second, but miles per hour. The wind is going 12 miles per hour, so it generates 10 kilowatts. How many kilowatts of power will it generate if the wind is going 20 miles per hour? So we have different units, but it doesn't matter. You still apply them the exact same way. Find A, plug that in for 20, and see what you guys get. And you can check with me, and I'll see how you did. All right, that is what this section is about. And we have finished. No way, we finished our chapter on polynomials. So hopefully you had a good time with it, and I'll see you guys later.